Hello students, it's Mrs. Denton and you are watching a video about the rotations on the coordinate plane. Let's get started. A rotation is a transformation that turns a figure about a fixed point. That turns a figure. So all a rotation is when you turn a figure to the left or right. Well, that fixed point is called the point of rotation. The point of rotation. And most of the time, in fact, all of the time for us, the point of rotation is going to be the origin on the coordinate plane. So the point 0, 0 is going to be our point of rotation. Well, when you rotate an object, when you turn an object, its image is the same size and the same shape, also known as being congruent, okay? So just because we're turning an image left or right doesn't mean that it's going to stretch the image or shrink the image. It's going to stay the same size and shape. The other thing to know is that rotations might be turning clockwise, which is why I have a picture of a clock here, or counterclockwise, okay? Clockwise or counterclockwise. It can be either direction. So gave you a little picture of a clock so you can remember the difference. Clockwise would be going this direction to the right. That would be a turn in the clockwise rotation, a turn to the right. This is actually considered negative rotation. This is considered negative rotation, okay? So we have not ever talked about a negative angle measurement, but there is such a thing, and that's because the negative is a direction. It's telling you to turn the angle clockwise or turn the figure clockwise. Counterclockwise is going against the numbers, okay? So counterclockwise is when you turn the figure to the left. This is considered positive rotation. Now, I know that might be the opposite of what you're used to, so that's going to be something to really think about. Clockwise rotation is negative. Counterclockwise rotation is positive. If there are no directions that say otherwise, you can assume that the rotation is counterclockwise. That way we're working in the positive direction. Okay? All right, so let's see what this might look like on the coordinate plane. When you look at a coordinate plane, it's broken into 4 quadrants. Hopefully you remember this from Algebra 1. We've got quadrant 1 on the top right. This is where everything is positive. Then we move to the top left, which is quadrant 2, where the x's are negative and the y's are positive. Then the bottom left is quadrant 3. That's where both the x and y is negative. And then finally, quadrant 4 on the bottom right, where the x's are positive, but the y's are negatives. Well, if we take a point, I'm just going to put it over here on the x-axis. If we take a point and we make one full rotation, one full revolution around the origin, we've created a circle. And that one full revolution is equal to a 360-degree turn. Now, we know that from previous studies. We know that one full rotation equals 360 degrees. Okay, so what would happen if you took that rotation and you only went halfway around the circle? Only went halfway around the circle. Let me get a different color. Well, what is half? What is half of 360 degrees? It's 180 degrees, and that's what gives us a semicircle. A semicircle is 180 degrees, half a rotation. It's also what produces a straight line, which we've talked about a lot. Well, finally, what if you only went around 1/4 of a revolution? You started here and you went 1/4 of the way around the circle. Okay, well, that's considered a 90-degree turn. 1/4 of 360 is 90 degrees. So these are going to be our three main rotations. We've got 0 degrees over here on the x-axis. If we turn 1/4 of a revolution, we're at 90 degrees on the y-axis. If we turn 1/2 of a revolution, we're at 180 degrees on the left side of the x-axis. And if we turn another 90 degrees, let's do that math. 0 plus 90 plus another 90 plus another 90 gets us at 270 degrees. That would be 3/4 of the way around the origin. And then all the way around gets us back to 360 degrees. What you are looking at is called the unit circle. And this is something that you're going to study in trigonometry over and over and over again. It's going to be one of the foundational pieces of trigonometry. So I'm really glad we're looking at it here as an introduction. When we're talking about rotations, we're using the coordinate plane, but we're overlaying this idea of a circle on the coordinate plane so that you can see the amount of rotation. Well, something I wanted you to think about is if we take a point and we rotate that point 360 degrees in the positive direction, we'll wind up right back where we were, 1 full rotation. So 360 degrees in the positive rotation gets us right back where we were. Well, if we take that same point and we rotate it in the negative direction, which is clockwise, so we rotate to the left, we wind up at the same spot again. Okay, so a positive 360-degree rotation is the exact same ending place as a negative 360-degree rotation. In trigonometry terms, this is called coterminal positions. I just want you to know that turning 1 rotation to the right is the same as turning 1 full rotation to the left. All right, let's use that 180. If we have a point on the x-axis and we turn it 180 degrees in the positive direction, which is counterclockwise, okay, we send it to the opposite side of the x-axis. So 180 degrees in the positive direction gets us to the left side of the x-axis. Well, how about 180 degrees in the negative direction? Check that out. Turn to the left. Again, it gets us to the same place. So a 180-degree turn in the positive direction gets you to the same place as a 180-degree turn in the negative direction. I find that pretty interesting. So that way you don't have to get hung up on positive versus negative. I've got the positive turns here in pink and the negative turns in blue. Now, I'm going to make a line here because things are about to change. Okay, let's take a look. Let's start over here again at that same spot, and let's turn it 90 degrees in the positive direction. Okay, 90 degrees in the positive direction would take us to the upper side of the y-axis. Okay, so a 90-degree turn in the positive direction takes us to the upper positive end of the y-axis. A 90-degree turn in the negative direction will not land in the same spot. How far do you have to go in the negative direction to land in the same spot as 90 degrees in the positive direction? Let's see what you came up with. Let's start here at our original point and start turning. I'm going 90 degrees in the negative direction, another 90 degrees in the negative direction, and another 90 degrees in the negative direction. 90 plus 90 plus 90 is 270 degrees in the negative direction. So a 90-degree turn in the positive direction is the same as a 270-degree turn in the negative direction. Okay? All right, let's think through one more here. All right, here I am again at that same point. And this time I want to take a 270-degree turn in the positive direction. So let's count it out. 90 degrees hits the y-axis. Another 90 degrees hits the negative side of the x-axis. And a third 90 degrees, 90 plus 90 plus 90, gets me to the negative end of the y-axis. So a 270-degree turn in the positive direction ends on the negative side of the y-axis. Well, how far do you need to go with a negative rotation to get to the same spot? To get to the same place in the negative direction, I would just have to make a fourth of a revolution moving in the clockwise direction. So that would equal a 90-degree negative rotation. A 90-degree negative rotation. So moving a fourth of the way around a revolution in one direction is the same as moving 3/4 of the way around the revolution in the negative direction. So check that out. Okay, next what we're going to do, if you flip over, we're going to actually move a figure. So let's take a look. Okay, so the first thing we're going to do is rotate the triangle in a positive 90-degree direction. Okay, positive 90-degree direction. So I recommend having maybe a few colors to do our next activity here. All right, so if I take this triangle and I rotate it 90 degrees in the positive direction, remember, positive rotation is actually counterclockwise. Okay, this is positive rotation. So if I go 90 degrees in the positive direction, what quadrant are we going to wind up in? 90 degrees in the positive direction is going to take us from quadrant 1 to quadrant 2. Okay, so we know our triangle is going to land somewhere over here in quadrant 2. So here's my suggestion. Draw a line from point A to the origin. Try to make it nice and straight. Grab a ruler if you need to. Okay, what is the slope of this line? Let's count it out. We just did a unit on slope. If I start at the origin, I'm going to count 1, 2, 3, 4, 5, 6 for the rise, and 1, 2 for the run. So rise is 6, run is 2. 6 over 2 can reduce to 3. So the slope of this line we just drew in is 3. Well, since I'm turning this 90 degrees, I'm going to use a perpendicular slope to draw another line in quadrant 2. So now we have to go back to understanding what a perpendicular slope is. So go back into your files here. A perpendicular slope is when you use the opposite reciprocal value of the current slope. So this is a positive 3. That means I'm going to need a negative. And the reciprocal is when you flip the fraction upside down. So this would be negative 1/3. So I'm going to count out a negative 1/3 slope into quadrant 2, which is where I know my triangle is going to be. So rise 1, backwards 3. Rise 1, backwards 3. This line, see if I can make a nice straight line here. Okay, this line is going to help me turn the triangle. Notice I've made a perfect 90-degree angle here. There's that rotation we're talking about. So now we want to plot the new point A on this line so that it's equidistant from the origin. Okay, so I had to go up 3, right 1, up 3, right 1 to get to A. So it should make sense that I need to go up 1, left 3, up 1, left 3 to find the new location of A prime. Okay. And then we just repeat this process for the other points. So I'm going to change colors here. Okay, I'm going to connect B to the origin. Nice straight line. Count out that slope. That's a rise 2, run 2. A rise of 2 and run of 2 reduces to a slope of 1. So the perpendicular slope is going to be negative reciprocal. Well, the reciprocal of 1 is still 1. So I'm going to make a negative 1 slope into quadrant 2. Rise 1, backwards 1. Rise 1, backwards 1. And B is going to land here. Equidistant from the origin. All right, and finally, I'm going to move point C. Again, use a nice straight line to connect B to C, or the origin to C, so that you can count the slope. The slope of C. Rise 2, run 1, 2, 3, 4, 5, 6, 7. Rise 2, run 7. So the reciprocal slope, this cannot be reduced, the reciprocal slope would be negative 7 over 2 to create a perpendicular line, the negative reciprocal. Okay, so bring it over into quadrant 2. I'd have to go up 7, 1, 2, 3, 4, 5, 6, 7, and backwards 2. 1, 2, 3, 4, 5, 6, 7, backwards 2. And this is my new location for point C. Let's see what happens when I connect all these dots. Ta-da! We've taken the figure that was once in quadrant 1 and rotated it 90 degrees around the origin, and it has landed in quadrant 2. It's the exact same size, it's the exact same shape, it's just been turned to land in a new location. Okay, next, we're going to look at what happens when we rotate something 180 degrees. I've got another set of points, another set of steps here. We're using the exact same triangle, so hopefully it will feel familiar. All right, so let's think about this again. This is, again, a positive rotation of 180 degrees. So positive rotation, we're going to turn half a circle in the counterclockwise direction. So what quadrant are we going to wind up in? We're currently in quadrant 1, so if we rotate 90 degrees twice, we're going to land in quadrant 3. So we're going to finish our picture down here in quadrant 3. So we're going to follow the same beginning steps. First, draw a line from A to the origin. What's the slope of this line? Well, we already did this up in the first problem. We got a slope of 3. Now, since we want to land in quadrant 3, I don't need a perpendicular line. I just need to come straight across. So continue using that same slope to draw a line from the origin into quadrant 3. All right, so this has a slope of 3, so I'm just going to continue with that same slope. Down 3, backwards 1. Down 3, backwards 1. So this line will pull me into quadrant 3. Plot A so that it's the same distance from the origin. So A is going to land here. 2 slope steps away from the origin. All right, switching my colors, let's find where B lands. First, draw in your line from B so that you can see the slope, okay? We've already counted this slope, so we know that the slope to B, it was 2/2, which reduces to 1. Now we want to stay with that same slope and pull the figure into quadrant 3. So stick with a slope of 1. And we'll find our new location for point B. Okay. Lastly, let's find the new location for point C. Draw a line from the origin to point C so that you can count the slope. We're getting a slope of rise 2, run 7. Same picture as the first time around. So we want to continue that slope down into quadrant 3. So that would be down 2, left 7. To find the new location of point C. Let's see what happens when we connect our dots here. Hopefully, we're going to have a congruent triangle. Okay, so once I connect the dots, I see that I have a congruent triangle. It's the exact same size and shape as the original triangle. It's just been rotated 180 degrees to land in quadrant 3. Our last example is going to be how to rotate a triangle 270 degrees. 270 degrees. Excuse me. Now, what we've previously talked about is that 270 degrees in the positive direction is the same thing as 90 degrees in the negative direction. So I'm actually going to rotate this triangle 90 degrees in the clockwise direction. That's a negative direction. That'll cause me, or that'll make a lot less work for me to do in the long run. Okay, so what quadrant are we going to land in if we take this triangle and rotate 90 degrees clockwise? Okay, so if you were working while I was working, hopefully you found that B lands at the point 2, -2. Here's what I've done. I counted my slope as a rise 2, run 2. That reduces to 1. The perpendicular slope is -1. So when I start counting out a -1 slope into quadrant 4, I land at the spot 2, -2. So the position for the copied image of B is at 2, -2. See if you can find the final place for point C. I got the final position for point C to be the point 2, -7. Let's connect our dots here and see if we've made a congruent triangle. Voila! We've taken triangle ABC from quadrant 1 and we've rotated it 90 degrees to land in quadrant 4. That 90-degree rotation is the same as a 270-degree rotation in the positive direction. Thank you for watching and happy studying.